It's great to be here. It's my first time in Israel, and it's first time in Tel Aviv, and it's amazing, guys. You guys built an amazing country, and it's so cool to be here. I will talk about creative AI, about serendipity and statistical learning, because I think, and I put the joystick and some pixels on the first slide because you probably played some computer games, right? And you remember back in the day, playing with computer was boring, right? If you were playing Counter-Strike, it was fun to play Counter-Strike against people, but it sucked balls to play Counter-Strike against computers because they were stupid and not creative. Now, when you tell this story to Garry Kasparov, he'll probably cry because in 1997 he lost to Deep Blue because he freaked out at some point when the Deep Blue made a move that he didn't expect. And the story goes that, in fact, this was a losing move for the Deep Blue. But Garry freaked out too much. And this is like the next step for creative decisions of computers. But it's not exactly creativity. However, if you look at the modern systems like AlphaGo or the chess system that Google developed, then they do play in a way that chess grandmasters find amazing. So the trick here is that all the systems are based on statistical learning. And statistical learning, by definition, is generalization of the stuff you saw before. So you see what is the controversy here, is like, how can you be creative if you learn on examples? If you learn on stuff that you saw before and then reproduce it again, it's by definition cannot be novel, but somehow it is. So there is the problem that we'll try to resolve and discuss today. And what do I do? So I have several projects, and today mostly I'll talk about the project we've co-founded with my friend Alexei Tikhonov. This is called Created Labs, where we study different applications of AI to art. And this is, for example, Petr Teremin. So Peter is the great-grandson of Leo Teremin, who invented this wonderful instrument, which is the first analog synthesizer. It is played through human's body due to the change of capacity between your hand and the antenna. It was created in Petrograd in 1922, and this is the great-grandson of the inventor who was playing on the opening of yet another conference in Moscow that was organized by Yandex, and for which we generated the melody that was then orchestrated by a professional composer and performed by a small orchestra with great-grandson of Teremin playing the lead thing. So we do some weird stuff with neural nets, as you probably gathered. Now, what else do? We do some research, and there are some papers, and if you really want to discuss papers, and I know some of you might, you can make a photo of this and just go and have a coffee and whatever. It's like the stuff that we'll go through is here. So we do different things. We do representation learning. For example, we recently published a paper that shows that you can use word embeddings to try to capture the connection between how the word sounds and what it means in English language. Because there is a lot of debate since prehistoric times about the fact that when humans were inventing language, they were using some basic sounds for some basic things. And the question is whether this symbolism still is present in the language. And we show that you can use computer science to try to generate hypotheses on that. And then these are two papers that I'll discuss today. This one about music generation, it's an old one. We did it like 4 years ago or something. And this one is a new one when we generated poetry. And I'll mostly talk about poetry today, but I'll talk about music as well in the end. And also I'm AI evangelist for Abbey. This is the company that does automated processing, document processing. So we do a lot of NLP and a lot of OCR and vision in order to streamline the bureaucracy, because everybody hates the bureaucracy, everybody hates documents and paperwork, and we also need forests. So it should be digital and it should be automated. This is basically what we do. Okay, so the outline of what I want to discuss today is as follows. First, we briefly will discuss what agent can be considered creative, what do we mean under creativity in general, what is the common sense notion, can we do some definitions here, and here also I hope that in the discussion part it would be nice to hear your ideas on that, because this is not a solved problem. And then I'll give some examples of AIs that people call creative. And then I'll give our own example on poetry generation, and we will try to discuss how generative models, so the models that try to generate something new, how can they actually do something that's fun for people? And we'll then try to wrap it up. Okay, so what is creativity? This is a difficult question, right? Because I think I started working on this topic like in 2013 or something. And what we did is we generated in Russian some lyrics that resembled the style of Russian punk rock singer Yegor Letov. Basically, he was kind of like Russian Kurt Cobain, but better. And so he's a cult figure among very small portion of Russian society that cares about very strange values of anarchy and punk culture and so on. And then we recorded a mini album that was called Neural Defense, because his band was originally called the Citizens Defense. So we published an album, and my favorite review of the album, we got like 300,000 listeners in the first week, and like it went viral and so on. But my favorite review was one of the guys said, "Why everything sounds so secondary? Why is it also secondary to the Letov's original work?" And we were like, "Dude, we just told you it's a neural network. It was trained on his lyrics to reproduce his lyrics. Maybe that's why it's so secondary." So what is interesting here is that humans perceive creative things as entirely human things. And even if you tell them that you did it with a robot, they still judge the robot like a not very talented human, you know? Which is not exactly how we teach ourselves. So when you teach your kid to draw, your kid probably draws you some outrageous shit. You look at it and you say, "Wow, you did really well." Because you know he's just 3, for God's sake. So you have different standards of estimation of creativity of your agent depending on the intellectual ability of the agent. But when we do something with robots, this doesn't happen. So when robots try to do something creative, we expect them to be more creative than creative humans, which is a very high standard. So this is the first thing I think we should remember about creativity. And another thing is that we define creative as something that's not measurable. We like to say that this is a priceless picture. Like Mona Lisa is priceless. We just do it historically. So it's very hard when you try to do some mathematics about it. People hate you a lot. So these are 2 factors that you should remember. But we are mathematicians, so we want to still do something. And people do a lot of mostly generative models to create some things that used to be considered human areas. So for example, we'll have a lot of examples later in the second talk about different applications of AI and how AI allows people to create. Here are some other examples. So with music, this is the piece that we generated and then it was orchestrated. So this is the opening of the conference. I'm not sure that video is very legible, but you can hear the music. Yeah, so we had like 3,000 people listening to the opening. That was very nice. But this was like one of the first tries, and then people start to, and actually people generate a lot of music with AI. The most known project that you definitely should follow if you're interested is Magenta, Google Magenta. And they got the best NIPS installation, I think, in 2016 for accompanying performance. So you could play with AI together. AI tried to jam with you. And they keep on working on the project. And there are also a lot of generative approaches that try to monetize generative AI in this context. For example, this is a Moscow-based startup called Mubert, or Mubert, I'm not sure how you pronounce it, but they do an amazing job, mostly recording samples from real musicians and doing combinatorics over them to create techno and lounge tracks. And then these two, Amper and Jukebox. Jukebox is probably the most well-known. This is UK-based Oxford startups that creates legacy-free commercial licensed tracks. So if you want to have a track to play in your, I don't know, commercial or in your corporate video or something, you can buy it much cheaper than from a real musician, and they're actually quite good. So these are generative applications, and there'll be much, like many more. So with video, there are a lot of interesting applications, and of course, video is basically merging with video games, right? Because Bandersnatch on Netflix is the example of a very bad video game, right? It's like a very bad video. If you like video games, you know that they're supposed to have to be different plots and like 700 different endings, and it should be all interactive, and you should be able to talk to a chicken in the corner or whatever. And Bandersnatch is just a very bad video game, in fact. But it's getting there. And of course, as probably you saw the deep fakes, the possibility to animate people in a very realistic way. Now, to produce something that's like, you know, where Ashton Kutcher actually plays 85 different plot endings, it's hard because Ashton Kutcher is fucking expensive. But this is why we need AI. We automate people and automate mundane tasks. So we capture all the emotions we need from Ashton Kutcher, and then we basically produce 64 different endings, and we make it finally a good video game with actual realistically moving people and so on. So this is where I think video is going in this area. But there are also commercial products, and like Convivo, for example, is the product for analysis of video through machine vision and some additional data tracking devices. And this is my favorite example of using AI. So do you have some friends who are photographers or videographers? If you do, raise your hands. Okay, some people do. And if you know somebody who's a videographer, you know that this person earns money making weddings. And this is the hardest thing ever when you aspire to be a creative person to cut wedding videos. Because wedding videos are basically the same thing all over. It's bride and the groom, the kiss, the doves flying in the air, and so on. So what naive guys do is they automate the process of video cutting for wedding videos. So this is, I think, is a fun example, but this is, of course, the first step, and hopefully further video production could be done to a large extent through automation. But now let's get a bit more mathy, and let's talk about one aspect of generation, and specifically, how can we generate language? How can we generate realistic sounding texts? And I think you all talk to your devices. Do you? I mean, it's not embarrassing. You can admit that. I talk to my device. And if you talk to your device, you know that your device is nice, but it doesn't sound too personal. It's very generic. The most boring person you know sounds more interesting than your device. And this is the problem that is not entirely solved. And when we talk about natural language generation, the question is whether we can, basically what we try to do is we have a lot of texts. We want to produce new texts based on the old ones that are not in our data sample. This is what we do through NLG, right? So, I mean, this is all formal, but the idea is that like corpus consists of text, and text consists of words, and then you have the vocabulary, and vocabulary size could be different depending on the size of your corpus, and so on. And then you want to have a model that typically, your model consists of two parts. This is not standard, but quite often it is. So that at first you have some representation learning, so you map your text or your words into some latent space. Usually it's an Euclidean latent space because computer scientists are lazy and they don't like any other metrics than Rn. They like proper metric spaces. And then out of it, you get another model that's generative one. This is quite typical, and this is what basically every autoencoder does. So do you guys know how autoencoder work? Raise your hands if you do. Okay, then I will not go through it, but this is the basic thing, and the question is now, why is it hard, and why is it harder than pictures? Because if you worked with vision, you could also see that now generation, when you talk with images, when you work with images, generation works much better than with text, I would say. Images are incredibly realistic for a lot of cases. And there are several difficulties. So the first one is there is a Zipf's law. So if you heard about Zipf's law, okay, I'll explain that. So Zipf's law is a very interesting empirical notion that when you work with your language, as the size of your corpus grows, the vocabulary grows exponentially faster. So you add more texts, but the number of words that are in your vocabulary grows faster than the number of documents that you add. This is because language is extremely excessive. We have a lot of synonyms and a lot of ways to say the same thing. So as we add texts, we basically increase the percentage of the words that occur only once in our training data set. Some rare words that were not there before start to be there, but we still don't know anything about them, because for statistical learning, it's nice to have more than one occurrence, right? So this is one problem that NLG, like natural language, generally has, and pictures don't have it. With pictures, if you add data, you get better performance. With text, this is not always true. Another thing is that we still don't know how to properly make everything continuous for the words. So if you have some autoencoder model, and okay, do you know how variational autoencoder work? What's the difference between variational autoencoder and a normal encoder? No? Yeah? Okay, just if you, maybe you forgot. So the whole idea for the variational autoencoder was that in actual encoder, you get this latent space, and there are a lot of empty parts in it. So you get some words here, and then empty space, and some words there. And then you need to sample from some area. Your model says, sample from here. But there are no words to sample. You try to take the nearest neighbor, but it's actually really far, and this is where you get a lot of mistakes. So the idea of variational autoencoder was to make a dense representation where basically all the words are mapped on a very dense cloud in your Rn, where you don't have these holes in your representation. This is the basic. You basically add some noise to make everything look really nice, and instead of the points, you start to have balls in this Rn space that start to overlap, and you basically add as much noise as needed so that your representation becomes dense. And this is improving the situation, arguably, also because then you can sample continuously out of this space. And the third thing is that if you try to do generation, you don't have objective metrics. People like art in a very different way. I like Malevich, my father doesn't like Malevich. And we have discussions, we have issues. So when you produce something that's generated, you don't know how to estimate it. So how do we try to approach this issue of generating language? We try to do it step by step, and today I'll talk about the first steps that we were through, and now we work on different models. But we pay a lot of attention to methodology, because when you try to research something and you don't have metrics, you should always control yourself, and you should always have a checkpoint to come back to, right? And finally, you validate with humans, and I'll talk about how humans perceive stuff. So what we did, and this is the paper that I'm talking about, so we wanted to generate poetry that resembles actual people. So we wanted to have poems that resemble poets, but are written by the model. And why did we want to do it? Well, we wanted to work with poetry because the data set was relatively small, but we had it. And the good thing about poetry is it's subjectively more expressive than text. So if you want to finally work with human peers to estimate the quality of your model, with text, it's hard to make people read a page of prose. but it's easy to ask people to read several poems. People find it fun. So we decided to focus on the poems. And the first trick that we did, and it's a relatively well-known trick, but if you want to do some stylization, it turns out that you shouldn't train your model only on one author. So you shouldn't, even the most prolific author is not good enough. So what we did, the first thing is that we were conditioning the model on the author we wanted to produce. So we were training language model based on the variational autoencoder, and we were conditioning it on the author in the generation phase. So as we were learning it, we were giving on every step the information about, now you're reading Shakespeare, now you're reading Bloch, now you're reading, I don't know, Mayakovsky, whatever. And then when we were sampling out of it, we were saying, give me some Shakespeare, basically. Yeah, and actually you could see that so obviously, if you train the model on Shakespeare and then you validate it on, let's say, Shakespeare, it gives relatively good results. It learns Shakespeare was a prolific guy, he wrote enough text, so you can train an autoencoder that resembles Shakespeare. But if you validate it on another author, of course, it's bad. But what is interesting is that if you start to train on the whole data corpus and then condition it on Shakespeare, then it not only performs really well on other authors, but it also performs better on Shakespeare. So the information about different authors in the data set help the model to learn more. So this is the first thing. The second thing is that as we were training it, we were using a very huge embedding. So basically it seems that we don't understand what information is meaningful for us and what is not meaningful when we read poetry. Because, we as humans perceive poetry on a very intuitive level. And then when we were trying to approach the generation of it, we thought, okay, we should probably be more meticulous about it and include all the information that's possibly there. So, but for word embeddings, for every word, we had phoneme information, so how the word sounds. And if we didn't have phoneme information, we were using some heuristical proxy and basically transcribing the letters of the word into how it sounds. Because for poetry, it's important to know how something sounds. And in English, for example, there are words that come from French that sound very different than original English words. So that was the embedding that we had, plus we were having the embedding of an author and of the document. And this is what we were feeding to the language model and training it on and then generating. And this is the raw output of the model. For example, this is Bob Marley. Yeah, this is without rhyming. This is just line by line generated output. What's a mystery? Turn me off. Let me know what I might do, because I guess we got better. It's kind of very hard to think. The boys are too fast to put another fight. We turn around and say we're never ready. Well, sounds a bit Bob Marley-ish, but not exactly. There is a man in the world. He's living in the crowd. I said it's gonna be fine because I hear you cry, hey, hey. Well, might be. And this is Eric Cartman. I specifically included it for Tel Aviv audience. So I'm not even a Jew. I've been fooled. I've got to leave this building, which is, I think, relevant in this particular case. And I came to know you already, dude. If that was such a special sheet by your parents, dude, they were gay. This sounds very Cartmanian, you know. We added Cartman just to text because well, Cartman is not a poet, but we thought that it would be a very good proxy to see if the model captures stuff or not, plus fun to see. Yeah, and this is Edgar Allan Poe. No fear is the only thing I wish to know. She knows her and how I feel for her. She will follow me into the eyes of the world. I fear the fearful sound through the night. You could see that Poe liked the word fear a lot, and the model learned that. But then you can go, of course, further with that. The good thing about this is that when a poet comes up with a line, he doesn't have to put the first line he came up with. He's trying a lot of different lines and choosing the one that he finds better. So what we did is we added rhyme and rhythm heuristic to this lines. So we did it the following way. We did just generation, a lot of text, as much as you want, basically. Then you randomly pick one line, and then you add a line that rhymes with it out of the whole bunch. Doesn't matter which line it is, just stick it to it, and so on. And then things got out of hand. The rose she saw was beauty shining, a flower full of gold, of silence and a warning that nothing told. That's a good poem. That's objectively good poem. Out of the awful world, a world beneath the sky, where people in the secret lie, and I in my garden of gold. Well, a bit, some grammar problems, but you know. Bob Marley. Yeah, I know that you can be something that I can't do. You got me feeling crazy. I'm giving everything to you. You know? Huh? In this jungle I stand up. I wanna turn free. Get the beat up to the top. And this is what I wanna be. And this is my favorite part, right? Kids have even learned the way to write B this way. Yeah, so this is fun, but we felt that we've made some progress. And yeah, of course, two things. So one thing is that, of course, this language model generates a lot of noise, so up to 30% of the lines are junk. You should understand that. So sampling this, we were doing it in a following way. We did it in a cherry-picking way, but it was not a severe cherry-picking. So we were sampling it line by line, and if the line was grammatically or syntactically not correct, we were crossing it out and sampling the next one. Okay? So it was random, but with some human filtering of objective rubbish. But it's fine, but how do you test it? So one idea that we had is to calculate cross entropy between the sampled author and the actual author. And this is the result that we got. It's relatively okay. So you have so here you have actual authors, and here you have generated authors, and here you have uniform random sample of the text of a given author, and weighted random sample. So you just randomly sample the words, just to self-check that your model is better than the random sequences of words with the corrected frequencies, okay? So first thing is that, yeah, all the models are better than uniform random or even weighted randoms. What is also interesting is that the model is usually showing lower cross entropy than author with himself. But this is the actual consequence of the Zipf's law that I've been talking about. So the model learns words that are more frequent, and author knows words that are special. So author with himself gives you a bit higher cross entropy than the model with the author. But still, it's more or less in a good agreement. There is the problem with Carroll, and the problem with Carroll reproduces itself with human peers. So apparently, Lewis Carroll, we thought that Lewis Carroll is easy to recognize, but apparently it's not. He wrote Alice in the Wonderland, but people don't read his poetry. So this is the test with human peers. Here is, what we did is that we presented 16 poems, 2 of each author and 2 of each network that was trying to resemble the target author. And every person had 5 possible answers to choose out of. Model or 4 authors: Shakespeare, Carroll, Marley, and Muse. And again, Carroll is hard for people, but you can see that people tend to recognize our Marley as Marley more often than actual Marley. And generally, all the others are like you have more or less a diagonal thing, and people quite often tend to recognize. So 30% of people say that it's generated Shakespeare when they are presented with actual Shakespeare, which is also showing the potential of human in this kind of tasks. So this is a semi-proxy for some sort of a Turing test for this kind of designs, right? And this is the quote that is not legible, but I'll read it for you. So Oscar Wilde once said that it takes a great deal of courage to see the world in all its tainted glory and still love it. So when I was working with this task and when we were going through tons of garbage and some really nice lines, we found constantly that something that's creative is very rare. Even in the generated output, it's also very rare. Now, humans have internal filter for this stuff, so if you come up with something that you want to sound creative but you feel it's not, you just don't say it. But the model doesn't have this kind of filter so far, so it gives us all the stuff, good and bad one. But we were not discouraged. We were thinking that, okay, so creativity is about serendipity. It's about luck. Let's assume that creativity is about luck. Because luck is something that we know a lot if we are mathematicians. You know, mathematics has a lot of tool to work with luck. So let's think about what can we do about creativity to model it. So one thing is that something is creative probably if it's on the tail of your distribution, right? So if you have a distribution of texts, mathematical expectation of a text is probably a text of an invoice. If you take humankind globally, then if you step in the several percents in this distribution, you get a contract. Then you move a bit further, and maybe you get some list of stuff to buy from the shop. Then you go a bit further, and you get a very bad love romance. And then you go even further, and then you finally get something good like Shakespeare or whatever. So you have to move out of your center of the distribution. But at the same time, you shouldn't go too far, because humans have problem perceiving complex things. So there is a mathematician, Misha Gromov, and I really advise, if you're interested in the topic, to see his talk, The Mathematics of Thinking, and it's on YouTube. And he says that humans do not, for example, accept sets that are bigger than 4. So if something that's bigger than 4, we split it into 2 smaller sets, so like 4 smaller sets or something. So there is a boundedness by complexity, and you can actually estimate it. So this is, so let's say you want to reproduce this distribution, right? And this is the distribution of something that's creative. This is Bach or Shakespeare or Joseph Brodsky, whatever. And this is what your model can do. And this is mutual information. This is how much your model captures of this original distribution. So you want to maximize this thing. But what is hard, it turns out, that for discrete sequences, this dependency, the interdependency within your data is actually timescale independent. So, and we managed to capture it on a plot, and it's a part of our preprint. The preprint is here. So let's say you want to generate music, not poetry, but music. And you can measure the mutual information between one note and another note that's played later in the same tune, okay? So let's say you play some C, Mi, I don't know, whatever, some notes, and then you make 10 notes step, and you measure what are the probabilities of different notes. And you find out that there is some mutual information between the distribution of the first note and the note number 10, and so on. And this is the plot that shows, so if you try to use just a language model to reproduce music on a huge music data set, this is how your mutual information decreases. So when you have node like 100, the mutual information is almost 0. When you have node number 1, it's almost 1. So the next node is almost always dependent on the first node and dependent a lot. But then if you look at actual data, and you start to have problems. So like this is jazz, for example. So this is how generated jazz, this is generated jazz conditioned. So we train the same language model and then we condition it on a style. And this is how the mutual information decreases for the generated output. And this is how it decreases for the real data, for the whole data set. So you see it basically flats out at some point. Which means that you can be very far in your sequence and still depend a lot on what's behind. And this is a huge problem with attention models and everything. This is why we have to use sec-to-sec for text and so on. Because somehow our brain manages to capture this and have some sort of elastic memory or something to address. So if you try to be creative, coming back to this notion of bounded by complexity, basically what you want to do is you want your model to be not declining further down, and you see, for example, if you look at the Bach thing that we generated, it was not behaving in a good way. It was almost flat. And if we were giving our Bach generated to people, they were saying, oh, that's too complex. You cannot pick the pattern. So it is there, it's just a very long one. And people get irritated with it. So there is some window between things that are too complex and things that are too easy, in which you want to stay, but also you want to have this window on the outer part of your distribution of whatever you want to generate. And I don't have final mathematical finalization of it, but I think this is an actual direction in which you can go and formalize creativity. So creativity is search for a part of your distribution that is far enough from the mean, but it's also bounded with complexity from below and from above. I wanted just to end the whole story with some basic notion of our experience. Despite the fact that texts are harder than music, you could see what, for example, GPT-2 now does, and you can see what Magenta now does, and so on. And there is a very good and optimistic feeling with that, I think, is that basically more data always helps. Despite the fact that it's difficult, but it seems that maybe all these technical endeavors are not needed. Maybe we just need to wait for 5 more years, and then just Moore's law and more data will help us to do these things nicer and better, even without more advanced understanding of how creativity works. Because we basically did it with chess, and we basically did it with Go, just by waiting for more data and more computational power. So maybe the whole point of this talk is just to learn something interesting and then wait for 5 years. I don't know. So yeah, and this is my estimation of how AI hype train looks. I like to end my talks with that. So people talk about AI a lot, and now majority of the money are in automation and in personalization, right? So this is where the money are. This is bullshit. It's getting bigger, so be aware and try not to reproduce it further. So if people ask you about like when robots will conquer us, consider this question seriously. This is important. When people, I do think so. When people ask you jokingly like, when will you develop robots that will conquer us, try to explain them to the best extent you can that you are not working on this. Because, or if you do, explain that you do, and to us as well. Because this is actually very important, because we see now as this hype is getting let's say self-enforced, it's getting bigger and bigger, and people start to freak out because of the things that they don't understand. And it's about us to explain them. It's very important. And I personally think that like these two things, generation and cognition, are basically gold and silver, but we don't do them really well yet. But I want to have less of this and more of that, and encourage you also to focus on these areas. Thank you very much. I'm ready for your questions.
You mentioned the GPT-2, so obviously, what's your opinion on the whole debate about the OpenAI not releasing the full model or only parts of it because it's too dangerous?
Well, who am I to teach OpenAI how to do their business? You know, it's their decision. I think that at some point somebody will release it, or somebody will release something that's better. I think that the biggest problem with fake news is not AI, is the problem that people don't have critical thinking and are not used to the idea of fact-checking. And this is something that you can change, but you should have social effort and you should have awareness of this problem real high. We know that's like global warming is a problem because for many years people who were involved in this area were talking to politicians and people that global warming is dangerous. Now we work in AI and we are affected by the fact that people have ignorant views about fact-checking and fake news, and I think we should get people aware that there is a problem in this area, and the problem is the lack of critical thinking of general public and some flaws of educational systems and so on. And AI can help with that actually. You can improve education, make it more effective, and allow people to develop more critical thinking skills, for example, through automation, so that the teacher has more personal time with the student one-on-one and all the mundane tasks are automated and so on. But this is a huge debate, and we should work on that rather than discuss a particular model that was released or not released by somebody, because the whole area is going forward really fast. And, you know, once it's there, it's there. Yeah, and also I have a inner, so I think that like thinkers, since the start of the world, there are two types of thinkers. There are scientists and shamans. And basically the difference between scientist and shaman is that shaman keeps knowledge as a secret and only allows a small portion of other shamans to share the knowledge, whereas the scientist is by definition the person who spreads the knowledge around. So, and I'm on the side of the scientists. I think it's the right thing to do. Yeah, sure.
I've noticed when generating rhymes,
Yeah.
that it was a very simple structure, like A,
Yeah.
B.
Well, this was predefined, so we were sampling it. So we were choosing the rhyming structure to sample with, and we were choosing it through estimation of the rhyming structure of the given author, and using the most probable ones.
Okay, so you managed to output some like inline rhyme or something more complex?
Yeah, it is possible. Well, the thing is that it depends. So this is why creativity is hard when you have statistical learning, because it's just about your sampling, right? You can generate 1 gigabyte of the data and then sample the stuff you specifically need out of it. So there's a question, what do? You generate more and sample better, or you tune the model to give you exactly what you want? And one of the examples that in the paper, we list some examples of faulty generation. And I was preparing them in a hurry because reviewers said, add us some examples. So I was, you know, 2 o'clock at night, whatever. And I dropped in an example, and I thought it's a faulty example because sometimes the line doesn't end. So I put a line that was like, at night I lay waiting for a. That was the end of the line. And then immediately when I put it on the poster, and there was a poster talk, and some guy came to me on EMNLP, and he's like, wait a minute, but this is a great one-liner. I'm like, okay. Because indeed, like if you think it's the whole poem, then it's actually nice. At night I lay waiting for a, and you have the feeling of longing, and that you don't know what the person's waiting for, and this is make you long for it as well, and so on. And actually, finally, this poem ended up to be published in a Journal of Modern Poetry in Helsinki. So creativity is tricky. But yeah, the inline rhyme is possible with these two things. Yeah, sure.
I have 2 questions. So at first, regarding the rhythms, I don't know, have you shown us examples of generated with rhythms? With rhythms?
With rhymes, you mean,
No,
or
not
rhythms?
rhymes, rhythms.
Yeah, so the rhythmic structure, it was trying to learn out of the phonetics of the line. So it was doing it line by line, but it had the phonetics information, so it knew where the stresses are. But it was picking the rhythm itself, so we were not specifically controlling for rhythm. It was just choosing the rhythm itself.
Okay, my other question
Uh-huh.
is now regarding the bigger the data, you said that it may not always help
Yeah.
in generating speed and generating
Language, yeah.
language. What is the situation right now? Does it help?
Basically, you pre-process the data in a way that you try to stick with like you pre-process the data in order to avoid dealing with rare part of your vocabulary. You cut it, basically.
Okay.
But still, quite often it helps, because you also need to learn syntax, and for syntax more data is better. And you also, for grammar-rich languages, I don't know, like let's say the language where the ending of the word changes depending on the gender, or you know, the adjective depends on the noun it's connected to, and so on. For these kind of languages, it's very important to have more data, because you have to learn this grammar out of it. Mm-hmm. Sure. That's it? There is? Okay, yeah, sure.
It's a little bit of off question. You had a claim there that people in general consider machines in whatever task they're doing with a theory of mind, so-called, as in supposed to be superhuman.
Either that or very stupid. Yes.
What is this based on?
The baseline?
No, what are you basing this on?
Well,
Did you guys...
Okay, so, all right. This is actually a very interesting and a long talk. I'm not sure that I entirely understand the question. But generally, the perception of intelligent agents other than humans is a very interesting topic on how humans perceive them. And you probably know about the uncanny valley myth and so on and so on. One of the basic examples I can give you is that Turing test is non-machine symmetrical. I don't know if you thought about it or not, but in Turing test, the person who's performing the test, the judge, is human. So machine tries to resemble human, and the human is the one to prove. If you reverse Turing test and make us to pass Turing test in front of two machines, so one machine is asking another machine and you something, and you try to simulate that you are a machine, you will fail. Because the first question the machine will ask is like pi into, I don't know, to the power of 10, and the machine will answer really fast and you'll fail. So this is the example of non-symmetricity of our thinking about intellectual agents in general. We are very human-centric. So this is my first notion, and it's not based on some statistics. I didn't perform some social research on that. But if you look at the uncanny valley, then again, it was the perception of uncanny valley was developed by a Japanese engineer who didn't do tests on humans. And what is interesting is that somehow sociologists tested it on humans 20 years after he came up with this knowledge. And in this 20 years, we got a lot of movies with clever and nice robots and a lot of cartoons about them. And so in the 90s, when they performed it on humans, they didn't find uncanny valley. And of course, this is the mystery that we would never solve. The mystery is, did we have uncanny valley before in the 60s and just moved it over with our own conscious, or we never had it to start with? And but yeah, it's mostly, my personal opinion is mostly based on circumstantial data that I sample from people around. And like, for example, voice interfaces is a very good example. If you talk to a person and the person doesn't get what you say, quite often you are getting irritated from the first try. So if you shout something to your wife from a kitchen and she doesn't hear, she's saying like, what? And you're like, oh, what did I tell you wrong? Yeah, come on, listen to me. You know, people get irritated really fast, and with machines they have the same level of tolerance. If a machine doesn't understand from the first try of what I say, people get irritated. Another, again, circumstantial evidence is this position of Andrew Ng. I don't know if you know him. He's the guy who developed machine learning course on Coursera, and he's famously saying that every algorithm makes a journey from being useless and stupid to being absolutely inevitable and really cool when the precision changes from 97 to 98%. You know. So, but I don't have representative statistics on that. You're right. Sure. Some more questions? Okay, then we're good.
Okay, thank you.